The second paper that we are going to have is the main author is at the same time the moderator of the industry panel discussion. He's Oliver Schwabe. He has teamed up with John Erkoyuncu and Essam Shehab. The paper that we are going to see is entitled On the Change of Cost, Risk and Uncertainty Throughout the Life Cycle of Manufacturing Products.
Hello everyone, my name is Oliver Schwabe, and this presentation provides a short overview of our paper on the change of cost, risk and uncertainty throughout the life cycle of manufacturing products. Okay then, let us get started. In practice, cost estimators typically assume that cost, risk and uncertainty continuously decrease across the whole product life cycle. Our research suggests that while cost, risk and uncertainty decreases between technology readiness levels or stage gates, it increases when technology readiness levels or stage gates change. This may then lead to the over and or under assignment of capital reserves over time, thus resulting in binding project capital unnecessarily and or the need to increase project budgets in an unplanned manner. Let us now explore the research effort and some preliminary findings. Let us start by revisiting some basic terms from the perspective of an aerospace manufacturing company. A risk is the single value impact and greatest likelihood of a threat or opportunity event occurring. Risks come and go during the life cycle. Uncertainty is the range between the best case and the worst case impact of a risk. The most likely value lying between these is commonly determined through policies and procedures. The confidence of certain values is commonly determined through statistical tools such as the Monte Carlo simulation. Quantification of risk and uncertainty is accomplished through a 3-point estimate, where the 3 points are taken as the 10%, 50%, and 90% confidence interval. This means that between the minimum and maximum estimated values, we have an 80% probability of being accurate. We therefore have an 80% confidence. The image then highlights that risk and uncertainty are the glue that connects the facts concerning business readiness to deliver on an estimate within its range of uncertainty, and the contingencies and reserves that are needed in order to arrive at a summary estimate a decision can be based upon. The next question we need to explore is how these risks and uncertainties propagate over time, both from an actual and perceived perspective. The concept most commonly applied is called the uncertainty funnel. The uncertainty funnel describes the relationship of estimate variability over the life cycle of a product or project. The variability is mapped on the vertical axis and time is mapped on the horizontal axis. The focus on the evolving perspective of time differentiates this perspective from the static perspective generally used by most estimates. Based on the example shown, the estimate variability, or if we take the difference between the upper and lower bands, the uncertainty of the estimate, decreases continuously over time. It is this mental model which our current research challenges. While the image suggests that promises, which are essentially commitments, should not be made early on in the life cycle, it is the purpose of the commitment which needs to be our object of focus. This purpose and the relevant acceptable range of uncertainty are described by the concept of estimate readiness levels. Estimate readiness levels, which are commonly termed ERL, are used to connect the purpose of a commitment with the acceptable range of estimate uncertainty. In this industry example, the estimate readiness levels 1 through 4 with their associated uncertainty ranges, termed precision, are considered as suited only for explorations and not for decision making. An ERL 5 is suited at a stage where information is requested, an ERL 7 for a request for quotation, and typically ERL 8 and 9 are suited for decision making. We do, however, also need to understand the underlying relationship between facts, assumptions, and risks before beginning to look at the manner in which such readiness levels actually progress over time. While ERLs provide a good summary of the evolution of the risk and uncertainty of an estimate over time, it is only when we examine the influence of facts, assumptions, and risks and uncertainties over time that we begin to understand that these do not develop independent of project management. In this figure, we see that over time, the amount of facts begins to dominate the estimate, therefore resulting in a low uncertainty range, while at the same time risks decrease and the assumption continuously acts as gearboxes converting risks and uncertainties into facts, or at least well understood assumptions. Based upon this understanding, we can now connect the concept of ERLs with risk and uncertainty over time. Key models describing the risk and uncertainty funnel are based on the work of Baumann in the 1950s, the American Association for Cost Estimation in the 1990s, NASA in the 2000s, and the constructive cost model COCOMO after that. The image maps the uncertainty ranges of the milestones or project phases in each of these models to the lowest common set of phases, as put forward by Baumann, which are the study phase, the concept phase, and the project control phase. The aggregation of the boundaries put forward by the models mirrors the initial cone of uncertainty introduced at the beginning of this presentation, although the overall picture tends to shift upward into a focus on high boundaries, therefore exceeding an estimate. This, therefore, is the paradigm of the uncertainty funnel as developed in literature and research. The question now is the degree to which this is reflected in practice. In practice, uncertainty is derived from risks at various points during a project. In industry, a common structure for a project revolves around a stage gate process that is shown left to right in the image. At gate 0.1, a concept is explored, and at gate 6.1, the project is closed. The image then shows how many risk-related questions are examined at each stage gate, whereby the amount of cost-related questions is shown at a lighter shade of gray. Please remember, every risk question results in assumptions and risks and then uncertainties. A risk may or may not be closed between stage gates. The stage gate model thus suggests that uncertainty may not decrease over time, since it continuously is re-injected at every stage gate. Let us now examine how we assess the magnitude of these risks versus only counting them. Assessing the magnitude of risks is done using a tool called the probability impact diagram as shown in the images. The table on the top shows scores for differing levels of probability and impact related to risk threats, therefore events that negatively impact performance. The table on the bottom does the same for risk opportunities, therefore events that positively impact performance. Each cell contains a number called discrete gross risk, which can be linked back to detailed scoring schemes. Discrete gross risk numbers are used to simplify comparisons. We can then apply the probability impact tool to the risks pointed to by the stage gate questions in an industry example. This table shows an excerpt of 10 risks from the risk register of an industrial project. For the first risk, the discrete gross risk value at gate 1.2b, which falls into the study phase of the generic phasing model previously introduced, was 22. The corresponding value of the risk of risk 2 was 8, and so on. The sum discrete gross risk value at gate 1.2b was 137, at gate 2.1b it was 129, and so on. Since risks come and go, not all risks had discrete gross risk scores at every gate. For example, risk number 3 was relevant at gate 1.2b, but no longer relevant at gate 2.1b. Let us now take a higher level view of the complete project risk register from this perspective. The image shows the sum discrete gross risk score for all risks relevant at each stage gate for an exemplary project. A trending line has been added to highlight how the sum score varies over time and indeed can increase from one stage gate to the other. Two examples are highlighted by the red frames. It is exactly this phenomenon which the previously introduced models for uncertainty funnels do not reflect, and which can result in the emptying of any budget reserves earlier in the project than planned. This points to a threat in applying the generic models. However, the good news is that estimators do appear to sense this, and this view is reflected in their understanding of the propagation of risk and uncertainty. The image shows the result of an ongoing survey of estimation and general business communities regarding how uncertainty propagates through a stage gate process. The degree of uncertainty for threats and opportunities is shown on the vertical axis. The stage gates are shown from left to right. Above and below the x-axis, the received answers are mapped to include a lower, upper, and average band. The answers are based on a survey, which you may have also participated in. The key insight is that although the uncertainty funnel model is widely propagated and influences decision-making, the actual perception of stakeholders is a very different one. A decrease in uncertainty over the course of a project is acknowledged. However, the degree of that decrease is significantly smaller than the funnel model suggests, while fluctuations are expected, especially around stage 3, where the first pilots and first series models are actually used in practice. This is of course common knowledge to a great degree. The moment a concept is actually trialed or used, the experiences seldom fully match expectations. This then brings us to the attempt at a summary model. If we now aggregate the initially introduced models of the uncertainty funnel, add the results of the community survey just presented, and also add the details of an internal aerospace company database for the propagation of uncertainty across the whole product lifecycle, we see a funnel that differs significantly from the initially introduced models and leaves room for the fluctuations between stage gates that exist as demonstrated by the research study. The noteworthy differences are the very high rate of uncertainty threat decrease during the early phases of the project, and then a leveling out of that decrease. Uncertainty opportunity remains significantly lower than uncertainty threat in absolute terms, and decreases much slower than uncertainty threat across the whole product lifecycle. This then takes us to some conclusions. Coming to the end of this short presentation, we can now summarize the research findings. 1. Risk and uncertainty fluctuate at and between stage gates or project phases. 2. The propagation of risk and uncertainty over time can be forecast. 3. Experienced estimators view the future differently than generic models propagated in research and industry guides. 4. Financial reserves or contingencies need to be revisited regularly to account for fluctuations at and between stage gates or project phases. And finally, 5. The robustness of a decision depends on the uncertainty range which is relevant at the time of decision making. Thank you for your attention. Any questions, please?
Oliver, thank you very much for sending the presentation and the paper, and also thank you for proposing the industry panel discussion around pretty much that topic that you are going that you were presenting to us. We are now getting Oliver live on that question and answer here. Oliver, hi, can you hear me?
Yes, I can hear you. Good morning, Franz and the team.
Thank you very much for sending the presentation and the video to us. I'd like to discuss with you a bit about the why of that method that you use. Can you report from a practitioner's point of view when there are indicators that should urge people to use this kind of methodology that you report about?
So yes, the big question of why is quite important. So in the conferences of CIRPe and in many spaces, lots of great innovations are presented, which are at the beginning of an implementation curve. And from an industry perspective, we use methods like this. They're nothing I've invented. They're used in large industries to plan the cost of projects, the budgeting, how uncertain are they going to be, how do we prepare for this. So any idea being presented in the conference is actually going to be budgeted for. There are going to be uncertainties involved, and we as a company need to be very careful about our cash and budgeting. And these show what the future of that cost estimate for any of the innovations presented is going to look like. That's why it's important for us as industry to understand how cost develop. Cost is always a plus minus. We have to pay for it.
Okay, so the question is then, okay, you have shown what kind of uncertainty is acceptable throughout the engineering process, throughout the project lifetime. But can you tell us a bit more in practice how you actually estimate these numbers and you relate them to the readiness risk readiness levels that you were presenting?
Yes, so absolutely. When you have two things. You have an estimate of cost, which is pieces of the work associated with it. And then you have risks associated with how accurate you are. If you say it's going to cost 100 euros, well, plus minus. There are risks associated with that. Risks lead to a plus minus. And when you aggregate them, it leads to this uncertainty about budgeted cost. And the main thing is that we all think it gets less, but actually in reality, it almost stays the same. So we as a company need to budget for this. Yeah. And at each stage gate, this is reevaluated, the risks, which leads to the plus minus in cost, the rest. And this is actually a very social human phenomenon. So this is not about technical things. This is about teams, it's about culture. It's about, do you want to take the risk with me of these lines? And that's very important. Human factors are critical. And we'll discuss this a little bit in the industry panel afterwards as well.
Okay. Can you give us some more thoughts about the factors that influence this uncertainty in practice? You were talking about human factors. How do you get people to not doing overly conservative assumptions in that risk? What are your experience about that?
Well, let's turn the word conservative into optimistic. So the biggest problem we have in engineering cost estimation is optimism bias, which says the engineers which make the cost projections, they feel really bold and confident that they're going to make it very cheaply. But experience shows that this is too optimistic, and it's a very human thing because this is the way engineers are. And even the UK Ministry of Defence says you have to correct every proposal for the optimism, the enthusiasm we all have at the beginning of our project, because when you begin deploying, reality hits, others get involved, and the risk grows.
Okay. I have one last question. I can see the live stream. Thank you, Grimpen Schmidt, for that comment that you have made here. It's a really interesting question, I think. It says, how do you estimate the effort put into the risk estimation industrial project? For example, how do you evaluate the risk of the risk management? Well, it's a really good question, I think.
At Rolls-Royce, we have data around this, and we can say very clearly that depending upon the total volume of the project and its complexity, you need a certain team size, you need to invest a certain number of hours to estimate in the first place. So turning the question around, in order to make a go, no-go decision on a project at the beginning, we have formulas, and reach out to me via email, that will say you need to invest, let's say, 5,000 hours for estimation. And if the customer is not willing to resource 5,000 hours, you have to say, well, I can only provide you with a lower quality estimate. Okay. And you shouldn't make a decision on that. So there are formulas, there is experience, it's team size, it's project size, and one can say to achieve a go, no-go decision, we have tables, happy to share, so much effort, so many hours with a team of 4, 5, 6 people, whatever.
Okay, thank you very much. I'm looking again to the chat whether something is going on there again. So I'd really propose to the commenting person, Grimpen Schmidt, get in touch with Oliver Schwabe. It's really easy to find him on LinkedIn, for example. Get in touch with him to have a more direct dialogue with him.
Happy to share.
Yeah. There. So thanks you. We are looking forward to seeing you again in something around 20 minutes. You're going to set up the industry panel discussion right now. We're going to solve that technically within the next 20 minutes to set that up. And then we're happy to see you and to see the panel. And we hopefully everything works technically. It's a bit tricky for all of us, and it's the first time. So we are all a bit patient if something doesn't work in the first minute. So fingers crossed, things work technically. We're really looking forward to see the panel, the discussion, and the contents that you're preparing. Thank you, Oliver.
Excellent. Talk to everyone in a moment. Bye-bye.
Bye. So that was the first part about risk and uncertainty estimation provided by Oliver Schwabe. You will see more of that in 20 minutes after the next presentation, where the industry panel discussion will take place. With a number of experienced experts from industry and academia that have a look at the estimates of costs and risks and uncertainty in industrial projects, and that's going to be applied to the research papers of this conference.